welcome.
Thank you everyone for coming here on this special occasion, the homecoming and almost the 60th anniversary for DSE. I have here pictures past, present, and future of this campus. So today I'm going to talk to you about uncertainty. I'm going to try to demystify some of the trickier parts of dealing with uncertainty and randomness. And this is something that I have done throughout my career. Like David said, I studied statistics and also some mathematics. And for both subjects, you know, all the time you have to make decisions under uncertainty, under randomness, and you have to rely on probability theory to think and reason about what you are doing. And I'll try to give you a glimpse of that, what we are doing, and give you a glimpse of probability theory through some interesting and kind of quirky examples that you will actually help me go through. And I want to make this lecture very interactive. Actually, you will participate. We want to test drive our interaction here. So I want to know a little bit about yourself. I want you to respond to this poll. This is an online poll. You can answer this poll through your cell phone. If you visit the web address pollev.com/sdamouras57. So if you go there, you will be able to respond to this poll, and in real time we will see the results. So we can all share the results and see what's happening. Now, I was hoping that everyone would have access to the internet. Most people now have cell phones and they have a data plan. Unfortunately, the reception here in this beautiful hall is kind of weak because we're in the basement. So if you don't have internet access, there are two ways to get internet. I made a Wi-Fi hotspot on my phone where you can log in. The name and password is called Homecoming 2024. This will only last you while we are here. If you want to have internet in general on campus for today, the university provides internet. You can text this code to the mobile number on screen, and you will get back a response with instructions on how to log in to the university's network, which is for every room. And if you go around, you will have internet. So, okay, the poll is already filling up. I'm going to give it another minute. Don't close the page we are answering because we will use that for what's coming up. Interesting things like vast majority is split 50-50 between alumni and current students or family. Have a few prospective students and party crashers, some people do your own level. Some people are still voting or working on their phone, so I'll give it another minute. Okay, so I think most of you have already voted, so it seems like 40%, 42% are current students. We have a lot of alumni and prospective students joining us. So that's excellent. Welcome everyone. It's nice to have this variety. I want to tell you a little bit about this talk, although April touched on this already. If I really want to describe this talk in one sense, I would say we want to see how people make decisions or examine how people make decisions under uncertainty. And there is actually evidence, people have examined that, psychologists, behavioral psychologists And they have shown that people are bad at it. When I say bad, I mean people have what are called biases, cognitive biases, wrong ways of reasoning about uncertainty. They get misled by different things, different perceptions they have, and this is actually proven. So they have done experiments, and also an example of a questionnaire or a question part of the questionnaire that shows that people make mistakes when reasoning about uncertainty. Right? When you reason about things that are certain, when you want to make a decision where you have perfect information, you just compare your options and you go for the best one, and everything is very straightforward, right? If you have many options, then you have to, it can get complicated. You can use optimization, and my colleague Andre is an expert in that, but in situations where you don't have uncertainty, things are relatively more straightforward. When you have uncertainty, things get more complicated. And actually a very good resource if you are interested in behavioral science and these cognitive biases is this book by Daniel Kahneman, who also won the Nobel Prize in economics for his work, Think Fast and Slow. It's an excellent book. So what we're going to do is examine some of these misconceptions, some of these biases. We're going to look at what are called fallacies and paradoxes. Fallacies are beliefs which are based on faulty reasoning. Paradoxes are statements that seem to run contrary to expectations. So I'm going to present some fallacies and paradoxes to you, and I want to see how you interpret them, how you perceive them, how you go about them, and then we'll try to explain what's happening and see how we should be thinking about these things. So really the talk, we have a way, we have a method of reasoning about uncertainty, which is the theory of probability, and I'm teaching courses on probability theory over the alumni, probably taking courses from me. So you can think of this course also as a sales pitch for the need for a theory of probability. We need the theory in the structured way of reasoning about uncertainty, because a lot of times our intuition can lead us astray. So we'll jump straight into it. I'm going to show you some of these examples. So the first one is actually an example taken from the research by Kahneman from the book I just mentioned. And here's how it goes. So we have Linda. The example is a bit dated, but I think it was a couple of decades ago, but here's how it goes. So Linda is a bright and outspoken 31-year-old who majored in philosophy as a student and was passionate about social issues. And you want to know which case is more probable. Is Linda a bank teller, or is Linda a bank teller who is also active in the feminist movement? Okay. So based on this profile, what do you think is most likely? Here of a potential Linda. This is actually from the digital archive of UTSC. You can visit that site. They have nice pictures of the history of the campus. So it seems we are like the third thing in the bank. It's more probable that Linda is a bank teller than Linda being a bank teller also active in the campus. Most people have already voted. Now we're getting closer to, it's not 50, it's like 40, 60. So let's say 60% of the people who voted and sort of think that Linda is a bank, it's more likely that Linda is a bank teller. 40% think that Linda is more likely to be a bank teller and active in the feminist movement. So the right answer is the first one, actually. It's more likely that Linda is just a bank teller, and the reason for that is because that option includes the second one. So this is a very common misconception. So actually, if you poll the general population, 80% would say, or at least that's the result when they run the experiment, 80% of the people responded that Linda would just be a bank teller versus 20% sorry, that C will be a backpedaler and active in the feminist movement versus 20% that it's more likely to just be a backpedaler. So the reason why just being a backpedaler is more probable is the following, and we can reason about that using a simple Venn diagram. I'm not going to use any math in this presentation. It's going to be only plots and diagrams. So a Venn diagram, you can think of a Venn diagram showing us the different options. So in one case, we have all the people who are backpedalers. The other, the red circle is all the people who are active in the feminist movement. And then you have the intersection, which is both statements. And you can see that the intersection in this diagram will always be contained in either one of these two cases, right? So if you think of a single case, that would be, like if there's a backpedaler, that would be more likely than having a backpedaler and something else, right? Having a conjunction. The same thing holds if you were comparing feminist versus feminist and backpedaler, right? So even though you have a specific profile, if you think about it, it's actually more likely to have the more general case. The more general case is more probable. Is everyone? Yeah.
So when we do like exams, we have an option for common or that's the Venn diagram, like the other thing we have to observe, right?
So, yes, if you have there will be an area. Yeah, but this is not asking what Linda is. It's more what is more probable, what is more likely. So you can ask this question and compare the two. And being a backpedaler will always be at least as likely as being a backpedaler in feminist.
This question is like the option in the question is subjective, like backpedaler and feminist. Like I think that maybe it would like I think a good question like can be the first A is like backpedaler, B is feminist.
But then I wouldn't be able to compare because one will not necessarily always get on the other. So I just put two options where we know that one always includes the other. All right? Okay. Sorry, I didn't hear. I just copied this question. No, I wouldn't. I hadn't defined, but I copied this question. This is actually the question that that was used in a psychology experiment. So I copied it verbatim, and it was from, I think it was sometime in the 80s when they ran this experiment. So. That is true, that is true. Although I don't think it would change, even if people interpret the feminist, who is included in the feminist differently, I don't think it would change the answer to the question because the conjunction, the intersection of the two would always be smaller than being a backpedaler. I agree with you that my definition or the boundaries of the feminist circle are not well defined, but even if people have different interpretations, it wouldn't necessarily change. It wouldn't change the answer. That makes. Sorry, I didn't hear that. Yeah. Here we don't need to be very specific about what the percentages are or what the population, the percent of the population actually is, because the answer will hold. It doesn't matter if 10% are feminists or 90% are feminists or what your definition of feminist is. Right, I'm going to move on to the next question. So this is called the conjunction fallacy. The title, actually, if you are interested in knowing more, you can Google it. There's, I think, for most of the slides I have, for most of the examples I have on my slides, there is a Wikipedia entry at least with that name. All right, we're going to move on to the next question. This is a question regarding a screening test. So what is a screening screening test? The screening test is a test, a medical test we take when we don't have necessarily symptoms. And we all became familiar with the screening test recently because we had COVID, so if you want to fly, you have to take the test before, or even if you want to see a concert and so on. Okay? So here's the situation. Let's say you have a screening test which has 90% accuracy. So what does this mean? It means that if you are sick, you will test positive with probability 90%, and if you are healthy, you will test negative with probability 90%. Okay? And let's assume that 10% of the population actually, at that current point, is sick with COVID. Okay? And you take this test yourself, and you test positive, and you want to know, if you tested positive, given that you tested positive, you want to know what are your chances of having COVID or having the condition of being sick. And I think we'll have a lot of alumni here as well. I'm more informed about probability than the average communication. So, let me give you a couple of seconds. Shaping up, we have roughly 50% of the people thinking you have 50% probability of being sick, 40% think you have 90% probability, and 7% think you have 10% probability. Now, the correct answer is actually the popular vote, is you have 50% probability of being sick. It's neither the prevalence of the disease, the 10% of the population, nor the accuracy of the test. Okay, and I'll try to explain why you have 50% chance of being sick using, again, a diagram. So this question, if you pose this question to the general population, most people would say that you have 90% probability of being sick because that's the accuracy of the test. That's how they interpret it. Okay, and this holds for many other tests that people are doing. But in reality, your probability will not be the accuracy of the test. You have to consider the prevalence of the condition in the population and actually combine them using what's called Bayes' rule, which I will not go into details, but I'll try to illustrate with an example with this probability. Okay, so here's our population. Let's say we have a population of 100 people. Okay, I didn't count them all when I was drawing this plot, but 10% of these people are sick. So I have 10 people on the bottom left in red, which are the sick people, and the rest are healthy. Okay. And out of these people now, if all of them take the test, here's what will happen. You will have 90% accuracy for the sick people, so 9 out of 10 people in the red will test positive. And you will have 90% accuracy for the healthy people, so out of the white dots, 90% of them will be negative, which I didn't draw minus signs, but I just drew the wrong result, the positive result. So 90% of the healthy people will test negative, and 10% will have a wrong test and will test positive. Okay? So in total, you have 9 sick people who tested positive and 9 healthy people who tested positive. Now, if you only know that you tested positive, basically this means that you know you belong in this group of people which have the pluses. You are somewhere in this group of people who tested positive. You could be healthy or you could be sick. And the question is, what are the chances of being sick? Well, you can see that out of this group of people, out of this 9 plus 9, out of this 18 group of people, half of them who tested positive, half of them are sick and half of them are healthy. So, in fact, your chances, without any other information, but only the fact that you tested positive, and given the other conditions, the other numbers for this example, the chances that you have the condition that you are sick, given that you test positive, is only 50%. Okay. If If you wanted to improve this accuracy, what you have to do is basically take another test, and once you have two positives in a sequence, then you can show that the probability of having disease is much higher. So that, that's why doctors typically, for screening tests, they will typically, even if you test positive, they will typically ask you to do a follow-up test to make sure, because the prevalence of the condition is low, then it might be a false positive, basically. Okay, let's move on to another question, a very famous one. So for this question, imagine you are flipping a coin independently, and you get 10 heads in a row. And you're wondering what will happen next. So if this is a fair coin, I have to specify here, this is a fair coin, and because they're independent, this is kind of jargon, but it basically means that the results will affect each other. You want to know what will happen to the next flip. If it's going to be more likely to be heads, tails, or it's just 50-50. So I think we're doing very well here. I might have given away the answer with the independently in brackets, but it seems like most of people think that it's 50-50. It doesn't matter what happened in the past. If you have independent flips, the next result shouldn't be affected, although it's a rare occasion to have 10 flips in a row, but that doesn't mean, if you know that your experiment is independent, your coin is fair, and your flips are independent, then it shouldn't affect the next result. Okay? Surprisingly, this is something that a lot of people get wrong, and intuitively you get that wrong, because if you see some rare occurrence, you think that somehow, the universe should make things even, and if you get like 10 heads in a row, the next one should be tails. This is a very common mistake that people do, and it's very subtle. It shows up. I catch myself thinking that very often. It's called the gambler's fallacy for obvious reasons. This is what people get when they are gambling. They think that if they lost 10 times, then the next time they are sure to win. God is fortune always owes it to them when they win. But in fact, it doesn't make a difference once you have seen what has happened. Okay, so this is called the gambler's fallacy, and it works whenever you have for example, an unbiased coin or a fair coin. Now the question is, because a lot of people, when they are gambling, they make this mistake. They think that they're going to win the next time. In fact, actually, if you're wondering how do we know that this holds, and because some people are suspicious, they think, okay, if a specific pattern, let's say in the roulette appears, then I know what's going to come next, or they try to find like intricate strategies of going about winning the casino or whatever. But let me tell you, for most of these games, at least reputable gambling, there is a statement where you obtain roulette. So I copied this statement from the Alcohol and Gaming Commission of Ontario for online gaming. When you have randomness in these games, the way they are set up, and there is a whole science behind it, how do you get like random draws from a computer, but basically people make sure that you have independent and random results that are not correlated in any way to other results, right? So that's a statement from the casino, or every casino, every online casino, that the random experiments should be independent. Okay? Now, if you don't believe they are independent, then basically the house is lying or the casino is lying, then you shouldn't be playing that game anyways. Right? So if people still believe that they can figure out what's happening because there are specific patterns, then this is very dangerous, because basically they believe that the casino is lying. Okay. And obviously statisticians don't like to gamble. Actually, there was a famous anecdote. There was a statistics conference. They organized it in Las Vegas. The hotel that was hosting the statisticians gave them a better price because they thought they were going to make money from the people gambling, but nobody showed up at the tables. People just attended the lecture and sightseeing. So we don't believe that much. There is also, from the Gambles fallacy, there is an inverse Gambles fallacy called the whole hand fallacy. Some people believe that if they win 10 points in a row or they get like 10 heads in a row, the next one will be more likely to be heads, which is not completely unreasonable, but under different circumstances. We'll see, I have another example. But again, if you have independent trials, then this is obviously wrong to have this belief. The hot hand belief. And here, if you're playing Russian roulette, unless you are rolling every time, it's not going to be independent. Okay, so in this case, you might be given a horse. You know, you only have 6 shots more. Okay, let's look at another variation of this coin flipping question. This is called, so this is a variation of a famous paradox. Let me explain first how it works. So you have the box that contains 3 coins, but they are not all fair. So one coin is fair, okay, it has heads and tails. The other coin has both heads, and the third coin has both tails. The way this experiment works is you pick one of these 3 coins out of the box. You don't know which one. You don't see which one you have, and you flip it once, and you get heads. And then the question is, what happens to the next flip? Is it more likely to be heads? Is it more likely to be tails? Or it doesn't matter, it's 50-50? Some people think it's more likely to be heads, the next one, some more likely to be around 10% each. Actually, I got it here. The right answer is the first one, okay, and by a wide margin. So let's see why. So we're going to look at this going through a tree diagram. So this is an example of a probability where we have a sequence of random experiments. So first, the first source of randomness is we pick a coin out of the box, okay? And we can pick a coin that has 2 heads, 2 tails, or heads, tails, each with probability a third. And then, from the coin that we pick, we're going to flip that, and we're going to get heads. So here I have all the options. So for each coin, there is 50-50 chance of seeing one or the other side. In some cases, they might be the same. Heads on both sides, tails on both sides. In other cases, in the middle case, it will be heads or tails. Now we know that the first flip is heads, so we're only going to focus on the top part of this tree, okay? Because these are the options that matter to us. We know that the first flip wasn't tails, so we're going to disregard the values at the bottom. And then these are the options you have for the second flip. The second flip can be heads or it can be tails, but there are many more ways in which it can be heads, because if the first flip was heads, it's more likely, relatively speaking, that you have a coin which is the biased coin which has double heads, and that will always be heads. Whereas for the fair coin, it can be heads or tails, but you will notice that for the second flip, given that the first flip was heads, the second flip, there are 5 chances, or 5 cases out of 6 equally likely cases that it's going to be heads, then it's going to be tails. So it's actually the probability is 5 out of 6 that it's going to be tails, right? So it's more likely that you get So if you want to take this to the extreme, think of this experiment where instead of just flipping once and getting heads, think of if you are flipping like 100 times and you get heads every single time, then what would you say about the next flip, right? It's more likely if you had 100 heads in a row, it's very, very likely that you got, almost certain actually, that you picked the coin, the biased coin that has two heads. So the next one will also be. Okay. Everyone? Okay, second question, yeah.
How is that right here? How's that right if you're ignoring the bottom distribution element?
You ignore the bottom because you are given the information that the first flip was heads. So the bottom one, the bottom part of the tree is what would have happened if the first flip was tails. So you know you are not in that part of the diagram.
Can I see the question again?
So if you pick a coin, flip it once, you get heads, and then you flip again. And then you ask whether the next flip is more likely to be.
So you usually have the same coin and flipping a second time?
Yeah. You don't go. Yeah. Sorry, I think maybe some people thought that you draw again.
Yeah.
Okay. My bad. So we have made that explicit. Anyway, you're not getting less than you're not getting marks. All right, so this is another one, and I think I'm going to end with this. Again, it's a variation on the same concept. Like you have a coin flipping experiment. So here you have a fair coin, okay, fair independent coin, and you flip it in a sequence, repeatedly, until you get one of two patterns. Until you either get heads, tails, or tails, heads, until the first time they appear. So here I have an example of the first 4 flips. Let's say the first flip was heads. You cannot have a pattern of 2, so you flip again, you get heads, tails. This doesn't match any of the 2 patterns. You flip again, you get tails, tails again. It doesn't match any of the patterns. You flip again, you get heads. So now the last 2 flips were tails, heads, and that matches pattern B. And then you would stop the game, and you would stop flipping. The question is, which of these 2 patterns is more likely to appear first? Is it heads, heads, tails, heads, or it doesn't matter? Kind of the same. Yeah.
Is it supposed to say heads, heads, tails, heads, heads, tails, tails? Like, what are the 2 patterns we're considering here?
We're only looking for these 2 patterns. If you get heads, tails, then you don't stop. You flip again, and then you try to see if you get the pattern, one of the 2 patterns that you have. So, for example, if I flip tails 5 times, I have to flip again because it doesn't match any of the 2 patterns. Is everyone okay with the question, the statement of the question?
So I have a basic question about the statement that so if it is a fair coin, how do we differentiate the fair coin between like each side should be like here, like no hand. So how do we if it is a fair coin, how do we define which hand is
if it's fair, then you have 50% chance of having heads or tails.
Yes. But there's no exception.
You mean in real life? Okay, it's more like a thought experiment. There are small variations. Okay, let's look at the answer. So it turns out, even though the patterns are heads, heads, and tails, heads, there seems not to be a big difference between the 2. Actually, one will appear, is more likely to appear before the other. So tails, heads is more likely to appear before heads. So we're going to examine this again with a diagram. So here we have the result of the first flip. We have 50% chance of heads, 50% chance of tails, right? But we know we won't stop here because to complete the pattern we need an extra flip. So for the second flip, there are 4 options, the 4 combinations for both. So you have, on the top you have heads, at which point you will stop. So heads will appear first. You can have tails. You can have heads, in which case you will stop because heads appears first. And you can have tails. Okay. Now, in 2 of these options you will stop. In the other 2, heads, tails, and tails, you have to continue. Okay, and if you continue with a third flip, you will see in some cases you have tails, heads appearing. In others, you don't have any of the patterns and you have to continue. What do you notice after, from the third flip onward? Is there any specific conclusion you can draw, or any regularity that we see? Yeah.
You're blocked from actually getting back to heads. There's
You
no way.
can never, after the second flip, you can never get heads again. The only option is to get tails. So either, because you end up with tails, either you get heads and then you have the pattern tails, heads, or you get tails, in which case you continue again with the next flip and the next flip. But no matter what happens, you know for sure that you will only get the pattern tails, heads at that point. Okay, you will only get it in the sense that it will appear first. Right? That will be the first one to show up. Okay. So even though the probability, if you flip the coin, the probability of getting heads is a quarter, the probability of tails is a quarter. When you look at them in sequences, actually one pattern is different than the other. And it gets even more interesting if you compare the opposite pattern, the one that I mistakenly had before. If you compare heads with heads tails, and you do the same analysis, you will see that the chances of each one appearing first is even, it's 50-50. But if you look at the slightly different question, if you look at the expected number of flips until the pattern appears, for heads, you will take on average 6 flips. For heads, tails, it will be 4. So they will have different expected number of flips, even though the probability of one of them appearing first is the same. For heads, and heads, tails. So I think I went a bit over. I had other examples, but I'm going to finish here. There are a couple of other paradoxes I want to cover, but I want to thank you all for your attention. Hopefully this convinces you of the usefulness and the interest in studying probability. And I want to thank you for joining us on this special occasion for the birthday of UTSC. It's the 60th birthday, but in terms of institution, it's actually, we are very young. I think this is the right picture for our birthday, and there is a lot of potential for UTSC, and it's very important to have a strong community to help us grow in the following years. Thank you.